Maybe I'll do it. We'll see. Okay.
Other homework?
Yeah, other homework now. Right, so we have here do you have the question in front of you?
Yes.
So what is, there's two energy levels I give you. The lower one, which is E1, minus 13.6.
That is E1.
Yeah. So this E1 is minus 13.6 electron volts.
Minus 3.4.
And the second energy level, E2, is minus 3.4 electron volts. Okay. How much energy is lost if an electron falls from 2 to 1? So the electron is here, and it falls to here. So how much energy is lost? Well, that's a simple subtraction. Minus 13.6. Well, yeah. Why am I even writing it down? 13.6 minus 3.4. Okay. So the energy lost is 10.1 electron volts. Is the difference. Yeah. In order to keep the energy conserved, the electron will release a photon. So now you have a photon that's released here. And my question is, what is the frequency of this photon? So E equals HF, F equals E over H, and we know the E from the previous part, but we must convert it into joules, and Planck's constant is number 6. So the frequency here, when we put in terahertz again, 2466 terahertz. 6 mega, 9 giga, 12 tera. 10 to the 12. Yeah. Right. While in energy state 2, a photon is fired at the electron, and the electron just about reaches energy state 3. So what happens now, if I go back up, I'll draw it again here, it's at 2, and this time the electron is here. It moves up because a photon is fired at it. And here this is minus 1.51 eV, and the previous one was minus 3.4 eV. So my next question then is, what is the frequency of this photon? So what do we do here? Well, again, we should work out how much energy was required. So that's 3.4 minus... Oh, you have it already, is that what you're saying? 1.89? Yeah. And again, our formula F equals E over H. So once again, will we do it in terahertz, since I did the last one in terahertz? 457 terahertz. Okay, right, so that's B part 1 actually. B part 2, what is the energy state 3? While in energy state 3, a photon is fired at the electron, and the electron is freed. How much energy is required to free the electron? Okay, so now look, the electron is now here in energy state 3, and another photon is fired at it. How much energy must this photon have to free the electron? While in energy state 3, look, here's the electron here, a photon is fired at the electron, still with me? And the electron is freed. How much energy does the photon need to free the electron?
More than 100%.
What do you think it is? No. No. No.
So we.
No. No. Put it down. Put it down. No. No.
Two.
No.
Minus 1.
No. No.
We.
1.89.
No. Stop guessing.
1.5.
Thank you. 1.51 eV. That's how much energy the photon needs to have, because the electron has minus 1.5 eV, so the photon needs to give it this much to free it. Remember from mechanics and from fields that negative potential energy represents something which is trapped. It requires that much energy to be freed.
You need to make it 0.
Yes. Zero energy represents a free particle under no force or motion. Yes? Yes?
Yes.
Yes. Right, next one. But we'll put that in joules for the crack. Right. 2.42 times 10 to the minus 19 joules. Okay, number 2 now. We'll have a look at that Kepler one too, okay? Right, an electron is accelerated through a potential difference of 10 kilovolts, and then it strikes tungsten. So what you have here is some kind of electric field with maybe a little gap here, and the electron is fired through the field, and then it hits some tungsten. And when the electron hits the tungsten, it releases a photon, as normal. Now the tungsten has a work function of 7.2 times 10 to the minus 19 joules. That. Now, if I put that in electron volts,
Should be small.
it's like the other metals, 4.5 electron volts, if you're wondering. Anyways, and the voltage here is 10 kilovolts.
You know that line?
Which line? This one?
No, the other one, the other one.
Hang on
Exact, that's exact line.
1 second, just let me put in the battery. So this is like the battery. Yeah, okay, this is the photon coming out.
It's coming out.
Yeah. Yeah. Okay. So, maybe if you look at your fields, you can remember some formulas for fields. So this is an electric field. Do you remember, or do you have the formula for the potential energy in an electric field? Q is charge, E is electric field strength, and D is distance. Q, E, D. But do we know the D? Do we know the E? No. We know the Q. What's the Q? Yeah, very good. Now, do you remember the formula for E? V over D. Now, just be a little bit careful. Maybe we should use different letters. This V is the distance the electron will have to travel, whereas in the formula, this D here is the distance between the plates. Yeah. But in this case, they're the same. So what happens?
Do we have plates here?
Yeah, that's how. Yeah. Electric field. KJ, you're not helping anybody.
I can't see the plates.
The black lines. You're not funny, KJ. You think you're funny.
So now the D is the same.
Yeah, it cancels. Yes, it cancels. So, charge of an electron is constant 23, and the voltage is 10,000. So the energy is 1.6 times 10 to the minus 15 joules. Now, when the electron is here, what energy does it have? Only potential. It's not moving. At the end, when it leaves the field, does it have potential energy anymore? No, it just left the field. It has kinetic. The potential equals the kinetic, like normal for these problems. So I can say kinetic energy equals this, so I can calculate the velocity. It will be, half mv squared is the, so if you multiply by 2, divide by the m of an electron, and then square root the answer. So the V is 59309,698 meters per second. Or if you want, that's 0.2 the speed of light, if you're wondering the size. Okay? But you don't need to do that if you just want to know how big it is. So it's going quite fast. Karar, focus, please. Now, this electron, what energy does it have here? Kinetic energy. Yes? And this kinetic energy will hit the metal plate and put the calculator down. Now listen carefully to this, okay? When a photon hits a metal plate, it will free an electron.
Okay.
The reverse is possible. If an electron hits and sticks to a metal plate, it will release a photon. You can, in physics, a lot of processes can be reversed. This is the thing about physics. So, if I can apply a force this way to make it move forward, I can apply a force the other way to make it move backwards. And remember, in fields, we can use a force to move a magnet to make a current, you know. But then you can move a charge to make a magnetic field. You know, like, you have this thing in physics where both directions are possible, with only a few exceptions. So what I'm saying here is, when the electron hits the metal plate, it will release a photon. It's just the reverse of what we saw earlier. That's what's happening. Do you understand? Yeah. So again, it's the same formula, that HF equals KE plus the work function, except this time we know the KE. There it is right there. And we know the work function. There it is right there. And do we know the H? We do. It's a constant. So if I divide by H, I can know what the frequency of the light is. 1.6 times 10 power minus 15 plus 7.2 times 10 power minus 19, and the constant is number 6.
What do you need frequency for?
Did I not ask for it? Well, what's the wavelength? So I need the frequency to do that. So it's a quite a big frequency. It's 2.4 times 10 to the 18. Can you write that down? 2.4 times 10 to the 18 hertz. Oh, come on. I'll have to use the pen, the mouse. 2.4 times 10 to the 18 hertz. Nailed it. Now that's only the frequency. Can you calculate the wavelength? So the wavelength would be C over this number. C is 28.
These
Constant 28.
oh,
So the wavelength, what did you get?
1.25 times 10 power minus
10 minus 10, yeah? Let me just turn my pen back on.
So that was 12.59.
My pen's not working. You can just write down. It's 1.24 times 10 to the minus 10 meters.
Yeah.
Now, as nanometers,
12.5.
0.12 nanometers. Wait, there's still one part left, but you don't need the calculator for it, so actually you can pull that up. The last part is,
What part of
what part of the spectrum is this? You might remember this one. Does anyone? It's a very small wavelength, 0.124 nanometers.
radio?
No, that's the other side. That's a big wavelength. X-ray. This is an X-ray that comes out. So this photon that you get at the end is an X-ray. And this is how they make X-rays in the hospital. This is exactly how they do it. What they do in the hospital is they have two metal plates in a big gun, and there's a 10,000 volts between the plates. A little electric heater releases an electron, and the electric field accelerates the electron. However, there's a small hole in the plate here, so the electron actually passes through, and then this electron hits some tungsten, and the tungsten is at 45 degrees. So here is the electron, and here's the tungsten, and there you are. So what happens is, the electron comes along and hits the plate and releases a photon, and then the photon bounces that way. And this photon is an X-ray. Then the X-ray travels through you, and only the bone can stop the X-ray. The rest passes through, and then you put the photographic material behind you. Where the photons do not hit, this part turns white, and where the photons do hit, this part turns black. And this is how you get the X-ray image of white bones and everything else is black. Okay? So you can actually see an X-ray machine is very, 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 very simple. And this is part of the reason it's been around for like 100 years. It's a very simple machine. Okay?
Isn't X-ray dangerous?
It is. Don't have one every day. Alright. Revision starts on Monday. I'm sorry we didn't have time for Kepler. Do you have class now? I don't? Alright, so you can stay and I'll have a look at your Kepler one.